We already have a few problems in the topic boundedness and related concepts, and we will continue with some more problems in this session related to boundedness, means supremum, infimum, etc. The first set of problems actually deals with what kind of change that can happen to supremum of a set if we modify that set by multiplying all its elements with a fixed real number or adding a fixed real number to all the elements in that particular set. The question is precisely the following. Let A be a non-empty subset of R that is bounded above. Let C belongs to R. So C is a real number. So the question is to show that supremum of C plus A equal to C plus supremum of A, where C plus A, the set is defined as the set of all C plus A, where A belongs to A. So from this set A, which is non-empty and it's bounded above, from this set we are actually forming a new set using the given number C, and that set we are labeling as C plus A, and it consists of all elements of the form C added to each and every element in capital A. So the question is to show that taking supremum of the new set C plus A is equivalent to taking the supremum of A, then adding C to it. So to show that, let us call the supremum of A. Let us notate the supremum of A by the symbol S. Let S equal to supremum of A, and S prime is equal to supremum of C plus A. So we have two notations. So what we are supposed to show is we have to show that C plus supremum is going to be equal to supremum of C plus A. That means we have to show that S prime is equal to C plus S. This is what precisely we have to show. So to show this, we can actually take actually in most of the problems like this, what we usually do is we will show that S prime is less than or equal to C plus S, and C plus S is less than or equal to S prime. That means one number is less than or equal to the other, and the other number is less than or equal to the first, and therefore both these numbers will become equal. So exactly the same procedure we are going to adopt here. So we have to show that supremum of C plus A is equal to C plus supremum of A. Now consider, let A belongs to capital A, then C plus A belongs to C plus capital A according to our definition. Now, what is the supremum of this A's? The supremum of A's is nothing but its supremum of A, we have assumed to be equal to S. Therefore, C plus A is less than or equal to C plus supremum A, that is equal to C plus S. So C plus A is less than or equal to C plus S, where S is the supremum of A. Now C plus A is an arbitrary element in C plus capital A. So we get that every element of the form C plus A is less than or equal to C plus S. Therefore, supremum of, in other words, this is an upper bound. That is the important thing. Therefore, C plus S is an upper bound for C plus A, because whatever C plus A we choose, that going to be less than or equal to C plus S. Therefore, C plus S is an upper bound for C plus A. But what is the property of supremum? Supremum is less than or equal to every upper bound. Therefore, supremum of C plus A is going to be less than or equal to C plus S, or S prime less than or equal to C plus S, which is equal to, no, that's we don't have to take that step. S prime less than or equal to C plus S. That's enough for us. So we have to show that S prime is equal to C plus S, and for showing that we established one side, that is S prime is less than or equal to C plus S. Now we have to show that the reverse inequality we have to establish, that is C plus S less than or equal to S dash. This is what we have to show now. What is this S prime? S prime is the supremum of S prime is equal to the supremum of C plus A. Therefore, whatever C plus A we choose, therefore C plus A is going to be less than or equal to S prime for all A in capital A. Therefore, A is going to be less than or equal to S prime minus C, obviously. Therefore, S prime minus C, remember that C is a fixed number, S prime is also a fixed number, but A is any number in A. Therefore, S prime minus C is going to be an upper bound for A. Therefore, S prime minus C upper bound for A. But what is the relation between upper bound and supremum? Supremum is going to be less than or equal to upper bound. Therefore, supremum of A is less than or equal to S prime minus C. But supremum of A, we named it as S. S less than or equal to S prime minus C, or C plus S less than or equal to S prime. So we established that C plus S is less than or equal to S prime, but we already have this inequality 1, this inequality 2. Therefore, both these inequalities together imply that therefore S prime is equal to C plus S. So we establish our claim. Now we will see another problem which is more or less similar, but here instead of adding C, we are going to multiply with C. Let A be as in the previous problem, that means bounded above non-empty. But C belongs to R is such that C is greater than 0. The question is, show that supremum of CA equal to C times supremum of A, where CA is defined to be equal to the set of all elements of the form CA, where A belongs to capital A. So here we have multiplication instead of addition. The steps are going to be more or less the same. Remember that we have assumed C to be positive. Otherwise, there can be some problem. So we are actually safe with that assumption. So we are going to actually follow more or less the same type of steps even here. Suppose S is equal to supremum of A, S prime equal to supremum of CA. We have to show that S prime is equal to C times S. This is what we have to show. So if we remember that what we have done in the previous problem, we have assumed, we have showed that S prime is less than or equal to CS and CS is less than or equal to S prime. Exactly the same procedure we are going to adopt even here. Let A belongs to capital A. Then we know that A is less than or equal to supremum of A, which is S. Therefore, since C is positive, we know that CA is less than or equal to Cs, because multiplication by a positive number will not change the direction of the inequality. Therefore, Ca is less than or equal to Cs. That is, Ca is bounded above by Cs, or Cs is an upper bound of Ca, or Cs an upper bound of Ca. But we know that all upper bounds are going to be greater than or equal to the supremum. Therefore, supremum of Ca must be less than or equal to Cs. Therefore, supremum of Ca less than or equal to Cs. But supremum of Ca we call as S prime. Therefore, S prime less than or equal to Cs. This is inequality 1. We established this. Now we have to show that Cs is less than or equal to S prime. Now we have to show Cs is less than or equal to S prime. We know that Ca, we know this. Ca is less than or equal to S prime, because S prime is the supremum of Ca. Therefore, since C is greater than 0, we can multiply with 1 by A on 1 by C on both sides without changing the direction of the inequality. Therefore, A is going to be less than or equal to 1 by C S prime. Therefore, 1 by C S prime is an upper bound for A, since A is arbitrary. Therefore, supremum is the least upper bound. Supremum of A has to be therefore less than or equal to 1 by C S prime. Supremum of A less than or equal to 1 by C S prime. But what is supremum of A? Supremum of A is S. Therefore, if you bring C also to the left side, C is less than or equal to S prime. This is inequality 2. Inequality 1 is S prime less than or equal to Cs. Inequality 2 is Cs less than or equal to S prime. So we established from 1 and 2 that Cs equal to S prime, or supremum of Ca is equal to C times supremum of A. We have another interesting question now. That question is the following. If C less than 0 in the previous question, suggest a similar relation between supremum or infimum of A and supremum or infimum of Ca. The question is, if C is less than 0 in the previous question, suggest a similar relation between supremum or infimum of A and supremum or infimum of Ca. So we have to think carefully, and here it's less than 0. Therefore, the inequality whenever we are multiplying with C, that will get reversed. We have to be careful about that. The next question is a little bit more interesting in the sense that the problem claims that whenever we have a set containing an upper bound of that set, that upper bound actually becomes supremum of that set. So the question is the following. Let A subset of R and let A belongs to A be an upper bound of A. Question is to show that A equal to supremum of A. That means whenever a set contains an upper bound of that set, that number, that upper bound becomes the supremum. Okay, we have to show that A is the supremum of A. let S equal to supremum of A. This is actually a very simple problem. Let S is equal to supremum of A. We have already the assumption that A is an upper bound of A. And what is the relation between supremum and upper bound? Then S is less than or equal to a very upper bound of A. Therefore, in particular, S is less than or equal to A. So since S is a supremum, it is less than or equal to all upper bounds. Therefore, S must be less than or equal to A. But A belongs to capital A and S is supremum and therefore S is an upper bound and S an upper bound for A. So if S is an upper bound for A and A belongs to capital A, then A must be less than or equal to S because S is an upper bound. So we have here S less than or equal to A and here we have A less than or equal to S. Therefore both together implies that A must be equal to S. So if a set contains one of its upper bounds, that upper bound must be the supremum of that set. And we have actually used an important property of supremum here. A and S are both upper bounds, and it is not actually possible that they are different because supremum is always going to be unique. That property also probably we have used here, and you just think that where exactly that property is used in this problem. Our next problem is the following. If A and B are two subsets of R, such that supremum of A is less than or equal to supremum of B, then show that there exists a B in B which is an upper bound of A. So supremum of B being greater than or equal to supremum of A implies that B contains at least one element that is greater than or equal to every element in capital A. That's what we have to show. So here we are expected to construct an element B in capital B that can become an upper bound for A. So just look at this expression. Supremum of A. In fact, here the inequality is actually strict. Then only it will work. This is otherwise it's not correct because otherwise you can take A and B to be equal, and therefore supremum of A and supremum B also can be equal. And in that case, we cannot actually say that this is going to be correct. So that's a mistake. So supremum of A is strictly less than supremum of B. So supremum of A is strictly less than supremum of B, and in between you can find, suppose that this is S1, suppose that this is S2. So S1 plus S2 by 2. See, this is actually a very what do you call common technique that we use in many problems, that to find an element between whatever two elements are, whatever two numbers are given, and make use of that particular middle element to prove something. So we have found one element S1 plus S2 by 2 between supremum of A and supremum of B. Now S1 plus S2 by 2 is strictly less than supremum of B. Therefore, can it be an upper bound? That's the question. Can it be an upper bound of B? Because supremum of B is the least upper bound. Therefore, S1 plus S2 by 2 cannot be an upper bound of B. Therefore, then S1 plus S2 by 2 not an upper bound for B. Now, this is not an upper bound. Suppose that we call this element as uh, we call this element as C. So, if this is not an upper bound of B, so C not an upper bound for B means that there exists some B in capital B such that C is not an upper bound. So C must be less than B. So just observe the relations now. We have supremum of A less than um, this is S1 less than C. This is less than supremum of B. But what is this B? B is an element of B. Therefore, this is less than B. This is less than or equal to supremum B. So we have supremum of A less than C less than B less than or equal to supremum of B. So supremum of A is less than B belongs to capital B. So this B is actually the element that we want because supremum A less than B, therefore uh, A less than or equal to supremum A less than B or A less than B. So we got an upper bound for A from capital B. And we can have several other problems like this using the properties of supremum, upper bound, lower bound, etc. And we leave a few exercise for you to solve in your own. And we will continue with our next topic in the next session.